on lattice and translation operations, especially fundamental translation operations. We have studied, and we have seen that there are two types of fundamental translation vectors, and we have studied the unit cell also. Okay, now today we will deal with basis and symmetry operations. Okay, what is basis? What are symmetry operations? Basically, we will deal with four types of symmetry operations, and those are translation, rotation, reflection, and inversion. So, basis and four symmetry operations: translation, rotation, reflection, and inversion. So, this will be the today's topic. Okay, so first of all, we will see what is mean by a basis. So we have seen a space lattice, and we know that space lattice is simply array of or an array of imaginary points where each point has identical surrounding. Okay, so the crystal structure is not an imaginary concept. It doesn't have imaginary points. On the other hand, crystal structure consists of atoms rather than the imaginary points, while space lattice consists of imaginary points. It's an array of infinite number of imaginary points. Okay, now space lattice is array of imaginary points where each point has identical surrounding. Crystal structure has atoms rather than imaginary point. Then how a crystal structure can be obtained from a space lattice? To obtain a crystal from a space lattice, we have to just put a, an atom or group of atom at each lattice point. That means each lattice point must be replaced by an atom or group of atoms. Such atom or group of atoms which when replaced by a lattice point gives rise to a crystal structure or form a crystal structure that is called as a basis. Okay, now important characteristics of the basis is that this group of atoms, what we call it as a basis, it is a building unit or structural unit, okay, of a crystal structure. So when a lattice point is replaced by this group of atoms, we find a crystal structure. So what is a basis? Basis is simply a group of atom that works as a building unit or structural unit for a crystal structure. So if one has to ask to define the basis, then you can define like the group of atoms which works as a building unit or structural unit for the crystal structure is called as a basis. In this way, in a space lattice, we simply put a basis. That means a point, every imaginary point in the space lattice is replaced by a group of atoms called as basis, and we obtain a crystal structure. Okay, so space lattice plus basis gives rise to crystal structure. So what is a basis? That can be understood from this mathematical relationship. It tells us that when basis is added to a space lattice, which is totally an imaginary concept, which is totally a mathematical concept, array of imaginary point, a mathematical concept. When a group of atoms is added, is placed at every point, imaginary points in the space lattice, we obtain a crystal structure. And crystal structure physically exists. So in short, space lattice added with basis gives rise to a crystal structure. And as we know, in the crystallography, we are dealing with crystal structures. Okay, so basis has its own importance. When basis is put in the at every point in the space lattice, we obtain a crystal structure. So in short, lattice is a mathematical concept, array of imaginary point. Crystal structure is a physical concept, okay, which is exactly a crystal, and crystal structure, which is a physical concept that can be obtained by a mathematical concept by adding a basis. Now, let us move to the next slide. Now here, I'm trying to explain the crystal structure that is obtained from lattice and base. Now here, this is a lattice. This is what we see here is a lattice, and to this lattice we have added a basis, and this, in this case, the basis is shown to consisting of two atoms. One is solid atom and another one is shown by an empty circle. Okay, so this lattice plus basis gives rise to crystal. Now what crystal structure, now what has happened is that every lattice point every lattice point is replaced by a group of atoms, group of two atoms. So this lattice point is replaced by this group here, this lattice point is replaced by this group, and in this way a complete crystal structure is built. Okay, now what is a basis and what a basis consists of? Okay, so what is basis? Basis is a group of atoms. It doesn't mean that always it has a group of atoms. It may be a basis may consisting of a single atom, or it doesn't mean that it always have a single atom. It may have atoms more than one. So it consists of basis consists of single atom or number of atoms, single atom or number of atoms. And how many number of atoms will be there? They will be as large as several thousand of atoms. Okay, so basis varies from a basis consisting of single atom to a basis consisting of not two, three or more, several thousand atoms. Okay, now if you are looking at the types of lattice, okay, you will find that there are only 14 types of lattices are there. Though there are only 14 types of lattices, how many crystal structures are there? Huge number of crystal structures are there which are physically available, and the large number of crystals possible is due to simply due to different types of bases. Since there are different types of bases available, okay, so we can find the large number of crystals. Now example is that if it is a single atom, that is called as monoatomic base. For example, a copper crystal, basis of copper crystal or base of copper crystal consisting of single atom. That means an copper atom is placed at every lattice point and we obtain a crystal structure, okay, of a copper. Okay. And complex bases which consisting of several thousand of atoms, those occur in biological material. So huge number of crystals are possible simply because of the variety of number of or different types of bases, wherein there are only 14 types of lattices, but since there are huge number of bases, we are possibly obtain the large number of crystal structures, or great number of crystal structures are possible. Now let us look at, after completion of the basis, we will see the symmetry operations. Now what do we mean by symmetry? Symmetry in general concept, symmetry is simply a line or is simply a plane, okay, that divides one thing into two identical halves, or that produces a same thing identical to original one. For example, a mirror is a plane, and that produces the image identical to the object. Okay, so that is again a kind of mirror. The plane of the mirror is a kind of symmetry. Okay, on the other hand, if we are looking at our body, it can be totally divided into two parts. In the, if we put a vertical line exactly at the center of the body, okay, and so that is again a symmetry operation, okay, that divides our body into two parts. So what is symmetry operation in case of crystal structure? One thing is important, that symmetry operation keeps the object or changes the object to itself, or it keeps the object invariant. Invariant means unchanged. The object remains unchanged or object remains invariant. So what is symmetry operation? Symmetry operation in case of crystal structure, symmetry operation is the operation which transforms the crystal into itself, or the operation under which the crystal remains invariant. Okay, it is one and same. The transforms into itself and remains invariant. Invariant means unchanged. Transform into itself means unchanged. Okay, so such type of operation is called as symmetry operation. Okay, so what is symmetry operation? The operation which transforms the crystal to itself, or the operation under which the crystal remains invariant, is called as a symmetry operation. Such type of symmetry operations are of four types in case of crystal structures. As listed
Let's
here,
start the
translation, rotation, reflection, and inversion are the four symmetry operations in case of crystal structure. In case of, lattices. So translation, rotation, reflection, and inversion. Okay, out of which translation is applicable to lattices only. It is not applicable to crystal. It is applicable to the lattices and two-dimensional bodies only. On the other hand, rotation, reflection, and inversion, these are applicable to all objects, including two-dimensional, three-dimensional lattices and crystals. Okay, so these three, rotation, reflection, and inversion, these three operations jointly define symmetry at a point in a crystal or in a lattice, and therefore these are called as point symmetry operations. Okay, so rotation, reflection, and inversion are the point operations or point symmetry operations. On the other hand, translation is the operation that is applicable to the lattices only. Okay, that means two-dimensional geometry. Okay, now, and important one, the last one, inversion, is not applicable to two dimension. It is applicable to the three-dimensional, that means crystals only. Okay, now what is a translation? The translation symmetry follows from the arrangement of the lattice. What is lattice? Lattice is a regular periodical arrangement of imaginary points. And since it is an orderly arrangement, that means regular periodic arrangement, it repeats itself after a certain period or after a certain distance in all directions. So in this way, we can find a position r prime defined by vector r prime from a position r simply by having a translation operation, such that position r prime is equal to position vector r plus operation t. Okay, so and both r and r prime having identical surrounding. Okay, so translation symmetry is possible in case of lattices because they have orderly arrangement, and it is just a repetition of a pattern after certain distance. So it can be mathematically represented as new position equal to original position plus translation operation. Okay, now let us look at the next operation, that is called as rotation. Now, what is rotation? Rotation means to rotate about a certain axis. To rotate about a certain axis. Now, lattice, when a lattice is said to be have rotation symmetry, when it remains invariant or it remains unchanged after rotating it about certain axis. Okay, about certain axis passing through a point or through a lattice. Okay, so if you have to define rotation symmetry, then we can define like this, that a lattice possesses rotation symmetry if its rotation by an angle theta about an axis, or in case of two-dimensional, it will not be axis, it will be simply a point. Okay, so about a point, and that transforms the lattice to itself. Lattice remains invariant or unchanged after rotation. Okay, lattice possess rotation symmetry if its rotation about certain axis by an angle theta will transform into itself, or lattice possess rotation symmetry if its rotation about certain axis by an angle theta will, okay, keep it invariant. Okay, so we are familiar with one thing, that every body or every object in the nature remains invariant about certain specific angle, and that angle is 0 degree or simply 360 degree or 2 pi radian. That means crystal remains invariant after rotation through 2 pi radian. So it means 2 pi, so angle theta can be obtained by the equation 2 pi equal to n theta. So what is theta? Theta equal to 2 pi upon n, where n is an integer, important quantity. N is an integer, and that is called as multiplicity of the rotation axis. Okay, so since the crystal remains invariant after 2 pi radians or 360 degree or 0 degree, so we can put 2 pi equal to n theta as a condition of invariance, and from that we can obtain the value of theta as 2 pi upon n, where n is an integer, and this integer is known as multiplicity of the rotation axis, where n can take the values 1, 2, 3, 4, and 6 only. These are the values which are only the values which are permissible for the multiplicity of rotation axis. Remember, the values greater than 6 and the value 5 is not here. 5 is not allowed rotation. Okay, now let us, why it is not allowed, we will see. But before that, let us go for one example. Suppose we have n equal to 6. Oh, it is allowed also. So what will be the value of theta? That will be 2 pi by n. That means 2 pi by 6. 2 pi radians by 6. What is meant by 2 pi radians? That means 360 degree upon 6. So 360 degree upon 6 means 60 degree. That means lattice repeats after 60 degree. Lattice repeats itself after 60 degree. Lattice repeats itself after 60 degree. Or lattice remains invariant after rotation about an axis through 60 degree. And that is explained. That lattice is shown in this figure. You will find that the object represented by a letter 7, okay, will repeat after a rotation through 60 degree. It remains invariant after every 60 degree. So this is a axis that this is an example of theta equal to 60 degree or n equal to 6. Okay, so you can have a three-dimensional figure that is of regular hexagon. Regular hexagon has n equal to 6 or theta equal to 60 degree. That means regular hexagon has uh, 60, it repeats itself or it remains invariant after 60 degree. Okay, now rotation corresponding to n is called as n-fold rotation, and the crystal or lattice is said to possess n-fold rotation symmetry. N-fold rotation symmetry. Thus, this lattice shown in this figure possess 6-fold rotation symmetry. Okay. Now, two-dimensional square lattice. If you are looking at the square lattice, a figure of square that has 4-fold rotation symmetry. Very simple. You draw the figure and you will find that it repeats after 360 upon 6. That means what? 90 degree. Each 90 degree. So it has 4-fold rotation symmetry. Now, as I have told to you, allowed values of rotation symmetries are 1, 2, 3, 4, and 6. That means n equal to 5 is not a, what you say, permitted rotation symmetry, or permitted 5-fold rotation is not permitted. Why? That we are explaining here. Okay, why? By using this figure. In this figure you will find that there are a, b, c, and d, 4 lattice points are there. Okay, and you will find that so the lattice points are periodically arranged, so they have a translation symmetry. Suppose that translation symmetry is translation operation in this case is represented by a vector t. So t is a translation vector. Okay, now suppose we don't know what symmetry is possessed. Suppose it has a n-fold symmetry. Okay, we have to consider one symmetry. Let us consider that it has a n-fold symmetry. Consider the lattice point B and C. Okay, if we rotate lattice point B in the anti-clockwise direction and lattice point C in the clockwise direction, we obtain the symmetrical lattice point B dash and C dash. Since it has symmetry, so we will have a symmetrical lattice point B dash and C dash, B prime and C prime, and B prime C prime. Since it is a symmetry, there is a translation symmetry exists. Okay, so b prime c prime, distance b prime c prime must be an integral multiple of distance bc. So we can write b prime c prime in terms of bc. So b prime c prime is written as integral multiple of bc, where m is integer. So b prime c prime equal to m into bc. Now look at the geometry of the figure. So since if this angle is theta, so this will be theta. Okay, opposite angles between the two parallel lines. So theta and theta. So if this angle is theta, then this will, and this is t. This is t. Why this is t? Because this is again a lattice point. This is again a lattice point, and the distance between the what you say period between the two lattice point is represented by translation vector simply. So it is equal to t. So if it is theta, it is t. The what will be this distance? This will be t cos theta. Similarly, so theta t, so this will be t cos theta, and if this is t, this will again be t. So what is b prime c prime? It will be t cos theta plus t cos theta. That means 2t cos theta plus t, and in terms of bc, it is equal to m into bc, so mt. So we have put here b prime c prime, and that is equal to mt, and that is equal to 2t cos theta plus t equal to mt. So that cos theta we obtain as equal to m minus 1 into t by 2t. That means m minus 1 divided by 2. M minus 1 divided by 2 simply. So t cancels. M minus 1 divided by 2. Now look at here what we have obtained. Cos theta is equal to m minus 1 by m minus 1 by 2. M minus 1 by 2. Where what is m? M is an integer. So integer can take any value from 0, 1, 2, 3, etc. etc. Okay. Now which values are permissible? The permissible values for m, integer m in this case, those can be obtained by, okay, those can be obtained by considering the values of cos theta. And which values cos theta take? It will take from 0 to uh, actually it has values from minus 1 to 0, minus 1 to plus 1. But if we take modulus of cos theta, it will have a values from 0 to 1. That means less than equal to 1. Highest value permissible is 1. Okay. So in that case, what will be the possible values for m? It will be 3, 2, 1, 0 and minus 1 only. Okay, that is it. And these values are of course corresponding to 0 degree or 360 degree, okay, 60 degree, 90 degree, 120 degree, 180 degree respectively. That means 1, this is 6, this is 4, this is 3 and this is 2. You will find that 1, 2, 3, 4, 6 are there, but there is no 5. Okay, so that means n equal to 5 or 5-fold symmetry is not permissible. Why it is not permissible? Because we have considered that if we consider that, we will not find a translation operation that will create or that will describe a symmetry. So compatible translation operation is not possible for 5-fold symmetry. So 5-fold symmetry is not, okay, not does not exist, or it is not allowed one. Okay, the what you say, the question will be there. Now here it is a simple demonstration, okay, by a geometrical figure. So here you will find that we have took the pentagons, okay, 1 2 3 4 5 angle figure, geometrical figure with 5 sides and 5 angles, that is called as pentagon. These pentagons are arranged to occupy a space, and important thing is that you will find that they does not occupy a space 100%. So these are empty spaces. These are empty spaces. These are empty spaces. That means they will not build up a lattice since they are not occupy the complete 100% space. So pentagons are placed side by side and do not cover a complete space. Therefore, why it is so? Because there does not exist the set of vectors A, B and C, fundamental translation vectors, that they will produce a translation symmetry T, so that, okay, there will be a translation. Okay, so therefore if we put the pentagon side by side, you will find that it will not produce a lattice. So penta, okay, so 5, n equal to 5 is not a, what you say, allowed symmetry. Now next type of symmetry is a reflection one. Okay, now what is reflection? At the beginning, I have told to you that there is certain plane that is called as the mirror exists, and it will produce a reflection of our any object on our face. Okay, and which is similar to object. Image is similar to object. Okay, so that is called as reflection. Now let us look at what is the reflection symmetry in case of crystal. In case of crystal, lattice possess a reflection symmetry. Lattice possess a reflection symmetry if there exists a plane or a line. In case of two-dimensional, which divides it into two identical halves. One is object, other is its mirror image. Okay, so that both are mirror images of each other. Now that we have tried to explain by using a notched wheel. So this is a wheel and a notch is created here. Okay, so this is a wheel. Notch means khas याठी कहने का अपन खास तैयार की. So this is a notch. So this is a wheel and a notch is created to a wheel, and this is the axis. Vertical line is axis, and that will work as axis of reflection. You will find that towards both sides of this axis we have the images, okay, which are symmetric to each other, which are invariant, which are remain unchanged after reflection. Okay, so since reflection is like a mirror, okay, like a jog possessed by the mirror, so reflection symmetry in crystals is denoted by M of the mirror, that is M. Okay, simply small letter M is the representation of reflection symmetry in case of lattice and crystal. Okay, so combination now without considering the simple mirror reflection or a reflection symmetry, we have to consider that rotation and reflection that appear jointly in case of the crystals. Okay, now how, if we consider reflection, allowed reflection along with rotations, you will find that there are two types of possible permutations and there are two types of possible combinations took place. One is rotation with reflection, and the second one is rotation without reflection. Okay, so in this way we find that for crystals or for lattices, there are 5 allowed rotations. Okay, 1, 2, 3, 4, and 6. Okay, and with these 5 allied rotations and possible reflections, we have 10 possible combinations of reflections and rotations, and these are 1, 1 m, 2, 2 mm, 3, 3 m, 4, 4 mm, 6, 6 mm. How will you remember this? If it is an odd number, that means 1, 3, okay, 1 and 3, you put it as 1 is possible, yeah, and 1 with a single m. If it is even number 2, 4, and 6, then you put 2 either, and if it is 2 with reflection, then put 2m, 2 mm, 4, 4 mm, 6, 6 mm, like this. Okay, so in all there are 10 combinations, okay, of rotations and reflection, where the number represents a rotation. So this is a one-fold rotation. This is two-fold rotation. Two-fold rotation. One-fold means it repeats after 360 degree, repeats after 180 degree, okay, repeats after 60 degree, repeats after 120 degree, and so on. Okay, so now here there are 10 what is a 10 possible combination of notched wheels are shown here. So you will find the same thing, same figure, okay, in your book also. Okay, so we have inversion, last operation, that is inversion symmetry, and you will easily understood from this image. Okay, it is applicable to 3D three-dimensional lattices only. You will find that R related to minus R for each lattice point. Okay, so in case of crystal, you will find here. Okay, so R, and it is denoted by a letter 1 bar. It is denoted by letter 1 bar. Okay, so this is possible in case of 3D. Okay, 3D crystals or 3D in case of crystals or 3D lattices only. Now, apart from this, there will be a combination of different operation, and best example is rotation inversion operation. So in this way, if there is a combination, then more symmetry will be there to a lattice. Okay, thank you, and here we are, okay, we conclude the session, today's session.